Welcome to Signal Ahead. I'm Alfred. Today's briefing, Cryptography, Academic, Thursday, August 06. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. Let me offer you a thought that cuts across nearly everything happening in this field right now. And it's this. The discipline we still call cryptography has quietly stopped being primarily about secrets. It has become increasingly a discipline about behavior, about what systems will do, under what conditions, when someone clever and hostile is standing just outside the frame. And if you only read the headlines, you'd miss that shift entirely, because the headlines are still full of the old vocabulary. Encryption, keys, ciphers, quantum threats to your bank, all perfectly real. But underneath, the center of gravity has moved. Let me show you what I mean, because it's the sort of thing you can only see when you look at a great many papers at once, rather than one at a time. Consider the classical picture. You have a message. You have an adversary who wants to read it, and cryptography is the art of making that reading impossibly expensive. The whole edifice rests on a clean adversarial model. I know exactly what you're trying to do, read my message, and I design against precisely that. The elegance of the field for decades came from that clarity. The threat was legible. Now, watch what happens across the current research. You have a scheme that hides secrets, not to keep a message private, but to lock the logic of a silicon chip. Homomorphic encryption repurposed so that a processor won't reveal how its own privilege. Switching works, even to the person holding it. That's not confidentiality of data. That's confidentiality of function. You have distributed point functions and function secret sharing, which take that idea and make it a first-class citizen. The secret being shared isn't a value, it's an entire function, splintered across parties so that no one holds the whole behavior. The object being protected has changed. And then look at where the anxiety actually lives now. Overwhelmingly, in these pages, the adversary isn't attacking encryption at all. They're attacking learning systems, and they're doing it by manipulating behavior so subtly that no secret is ever broken. There's a backdoor that stays perfectly dormant, invisible, doing nothing wrong, until someone requests that a few training records be deleted, and only then does it wake up and turn malicious. There's poisoning that preserves the exact count of every event, so the tampered data looks identical to clean data once you aggregate it, and yet the model's temporal reasoning has been quietly rewired. There's an attack that doesn't try to make a network give wrong answers at all. It makes the network give right answers while burning through its energy budget, inflating power draw on a battery-powered chip until it dies. Correctness monitoring never flinches. Do you see the pattern? These are cryptographic problems, but the currency isn't secrecy, it's assurance. Can I trust what this system will do? And the old tools, the ones built to protect the message, are not built to answer that question because the attacker here isn't reading anything. They're behaving. They're piggybacking a malicious instruction onto ordinary speech so an audio agent hears an order the human never gave. They're poisoning a memory system so that a compromised instruction stored today gets faithfully recalled and obeyed weeks later. The threat has become semantic, temporal, and it hides inside legitimate operation. Which brings me to the thread I want to follow through the rest of our conversation, because I think it's the most important development in the field and the least appreciated. As the thing we are protecting shifts from secrets to behavior, the mathematics has to shift too, from probability to proof. When your adversary was trying to read a message, you could reason about how many centuries of computation they'd need. Statistical, bounded. But when your adversary is trying to make your system misbehave in a way that looks like correct behavior, you can't measure that in centuries of computing. You have to say precisely what the system is permitted to do and prove it can do nothing else. That's why you now find proof assistance, the machinery of formal mathematical verification, pushing into cryptography, into secure compilation, into certification. That's why people are formally modeling the access control rules of a cloud IoT platform and asking an automated solver whether information can flow between two devices that were never meant to talk. And it's why one of the sharpest results in this whole collection is essentially an impossibility theorem, a proof that useful capability, reliable safety, and open access simply cannot coexist when your only evidence about someone's intentions is the sort of thing they can copy and fake. That is a cryptographer's instinct applied to a world without secrets, and it is, I'd argue, where the whole field is heading. So over our next two segments, I want to trace that migration carefully, first into the machinery of proof, and then into the strange new adversaries that made proof necessary in the first place. If you glance at the surface of this field as it stands, you would be forgiven for concluding that cryptography has fractured into 1,000 unrelated skirmishes. Here is a scheme for locking the logic paths of a silicon chip so that an adversary cannot resurrect a stolen design. Over there, someone is smuggling malicious instructions into the ambient hum of a room so that a voice assistant, hearing what it takes to be its master, quietly executes an attacker's will. A third party is poisoning the training data of a spiking neural network in a way that leaves the labels honest and the aggregate counts identical, so that the treachery is invisible until precisely the moment it is invoked. It looks like chaos. It looks like a discipline pulled in every direction at once by the sheer proliferation of things we have built and now must defend. But I want to suggest that beneath this noise there runs a single deep current, and once you feel it, the apparent scatter organizes itself into a story with a definite direction. The current is this: the boundary we are trying to secure has stopped being a wall and become a process. For most of the history of the subject, security had a wonderfully clean geometry. There was a message, there was a channel, there was a key, and the adversary lived on the outside trying to get in. You drew a line, you proved that crossing it required solving some problem believed to be hard, and you slept soundly. The line was static. The secret sat behind it. What the present body of work reveals, almost against its own intentions, is that this geometry has quietly collapsed. Consider how many of these efforts are no longer defending a point in space, but a passage through time. There are backdoors designed to lie dormant, doing nothing, betraying nothing, until a perfectly ordinary act of data removal, the kind we now perform in the name of privacy, flips them awake. There are attacks on the memory of an agent, where the poison is planted early, persists quietly, and detonates only when recalled many interactions later. There is the modeling of attacks on power substations not as single intrusions, but as phased strategies, where the meaningful object is the whole arc from reconnaissance to actuation, and detecting an isolated symptom tells you almost nothing. In each case, the thing under threat is not a stored secret, but an unfolding trajectory. Security has become temporal. And where it is not temporal, it has become distributed across a supply chain that no one party controls. Notice how frequently the attacker in these accounts is not the outsider at the gate, but a compromised component already inside the tent, a poisoned open-source library that has smuggled private training data directly into a model's parameters, an inference time harness whose hard-won engineering can be distilled away by a rival, a cloud access policy that is individually correct on every device, yet permits a catastrophic flow of information when you trace the graph of who can whisper to whom. The vulnerability lives in composition. Each piece behaves. It is the assembly that betrays you, and no single custodian ever sees the whole. Now, if that were the entire story, it would be a council of despair, the perimeter dissolving, the adversary already inside, the moment of compromise smeared across weeks. But the same current carries the response, and the response is genuinely beautiful. If the boundary is now a process, then the guarantee must attach to the process itself, not to its edges. This is why formal methods and proof assistance keep surfacing, why people labor to model an entire cloud service formally and then let a solver reason about every possible information flow, why there are frameworks that reason over the hierarchy of known weakness classes to generate the very properties a hardware module ought to satisfy. The instinct is the same in each. Stop guarding the wall and start proving things about the machine's behavior as it runs. And crucially, the cryptographic toolkit is metamorphosing to match. Look at what distributed point functions and function secret sharing are actually for. They let you split not a message, but a function across parties, so that computation itself becomes the secured object, the private query, the correlated randomness generated ahead of time, the aggregation that reveals a sum while hiding every summand. Look at secure aggregation, letting hospitals train together on clinical brainwave data without any of them exposing a single patient. This is cryptography that has abandoned the static secret and embraced the living computation. It secures verbs, not nouns. So here is the deep current, stated plainly. We spent decades learning to hide things. We are now learning to guarantee behaviors over time, across composed and partly untrusted parts, inside systems that learn and remember and act in the physical world. The one hard limit standing over all of it is the trilemma I want us to hold on to. Useful capability, reliable safety, and open access cannot fully coexist when the evidence you rely on can simply be copied. That tension, I think, is where the third part of our story must begin. If you have been with me through the previous hours, you will recall that we traced a single thread, the migration of security's center of gravity away from the algorithm and toward the assembled system. Now I want to ask what that migration means, not the mechanics of any one attack, but the shape of the world it leaves behind. What should you watch for, and why does it matter beyond the seminar room? Begin with a striking symmetry. There is a recurring observation that the very properties we introduce for the sake of efficiency or capability become, almost mechanically, the surface through which we are harmed. Consider the spiking neural network, prized precisely because it stays quiet, it fires sparsely, it sips energy, it is beloved of the always-on device running on a coin cell. And yet that sparseness is exactly what a sponge attack exploits, deliberately provoking activity to drain the battery, and doing so invisibly because the answers remain correct. Nothing is wrong with the output. The system is simply being made to work itself to exhaustion. The lesson generalizes. A system that is only ever monitored for correctness cannot see attacks that live in the margins, in energy, in latency, in timing. If your alarm only rings when the answer is false, an adversary who leaves the answer intact walks past you entirely. That is the first thing to watch, the drift of the attack surface from the semantic to the physical, from what a system says to how it behaves while saying it. We see the same drift in the world models that give embodied machines a predictive core. Once a system compresses its perceptions into an imagined future and acts upon that imagination, a corruption introduced far upstream, in the data it learned from, in a sensor reading, in a stray instruction, can propagate all the way into motion. The threat is no longer contained to a screen. It reaches into the physical envelope, and it can lie dormant across the entire life cycle before it expresses itself. And dormancy is the second theme worth your vigilance. There is a genuinely unsettling development in the design of backdoors that do nothing at all when implanted. They show no elevated success rate. They pass every behavioral inspection and only awaken later, when some ordinary sanctioned operation is performed. A request to unlearn a record, framed as a privacy courtesy, becomes the very act that arms the weapon. The camouflage is not merely quiet, it is designed to be removed on schedule. This should trouble anyone who imagines security as a checkpoint you pass once. The clean sample and the poisoned sample can be made identical after the point where you look at them, differing only in an ordering you never inspect. Verification, at a single moment, under a single lens, is precisely what these constructions are built to defeat. Which brings me to the deepest of the second-order implications, and it is almost philosophical. There is an argument that safeguards resting on copyable evidence cannot deliver reliable safety, that when the only thing distinguishing an authorized professional from an attacker is context the attacker can simply reproduce, you are forced into a trilemma. You may have useful capability, reliable safety, and open access, but not all three at once. That is not an engineering shortfall to be patched next quarter. It is a structural constraint, and the proposed relief is telling. Introduce something hard to copy, a trusted credential, information that actually predicts downstream use. In other words, safety migrates from what is said to who is speaking and why, from the copyable to the unforgeable. So what, taken together, are we to make of it? I would offer this. The field is being pushed toward a security that is continuous rather than punctual, contextual rather than local, and grounded in something that resists duplication. You cannot secure a permission in isolation when devices hold different levels of trust. You must reason about the flow between them across the whole graph. You cannot certify a component. You must reason about its life cycle, its memory, its supply chain, the harness that coordinates it. And against all this, there is a quieter, hopeful countercurrent, the growing insistence on formal proof, on modeling systems precisely enough that a machine can check our reasoning, and on primitives, like the lightweight sharing of secret functions across parties that give privacy without demanding trust in any single custodian. Watch then for three things in the years ahead. Watch whether monitoring learns to see behavior and not merely output. Watch whether verification becomes something we sustain rather than something we sign. And watch whether we can supply the unforgeable credentials, proofs, distributed trust fast enough to matter. The algorithm was never the whole story. The system is the story now, and the system, unlike a cipher, is never finished being attacked. That is a sobering place to end, but not, I think, a despairing one, for naming the shape of a problem is the first honest step toward living within it. That's the signal for today. The noise will keep coming, we'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.